Yeah, I don't know how to do. I don't know how to do a backup of my recording. It basically takes a long time to render it after I'm done, so I'm nervous about what exactly might happen. Okay, so let's look at a pass transistor. Let's see, make sure I draw this in a logical way. The case that's problematic. So I've got VDD here. So I'm trying to pass a logic 1, and I've got a signal. Okay, so I start at 0, and I want to switch. This input swings to VDD. And I'm looking at this node. What happens to it? Okay, so let's just draw the answer to start with. It rises quickly for a while, then it tails off, and it does stop at about VDD minus V threshold. Okay. Okay, now why does it, and maybe I actually, the case you're curious about is you're saying 2 pass transistors in series. Okay, so let's do that. Okay, so we've got point A and we've got point B. And we'll see if I derive this all correctly. So it's one of the ones where I know the answer. Now we'll see if I can derive the answer correctly. Okay, so our transistor equation is the drive current is proportional to constant times VGS minus VT to some value alpha. Okay, so classically that was 2. Modern processes is more like maybe 1.5 or so. But it doesn't really matter. The key thing is that our current, as long as VGS minus VT is positive, our transistor keeps driving current. It's still on. Okay. Once VGS minus VT equals 0, the drive strength goes to 0. The drive current goes to 0, and we stop changing, the output of this transistor. Okay, so let's go through what happens in all these voltages. So this is my when you're operating in this mode, think of this as being your drain, and this as being your source. So let's just do VA first. Okay, so this first trend, and let's call this transistor 1, and we'll call this transistor 2. So transistor 1 has VGS1 is equal to VDD minus VA, right? So the current of transistor 1 goes to 0 when basically VGS1 minus VT equals 0. And that means VDD minus VT minus VA equals 0, which if I reorder things, that happens at VDD minus VT equals VA. Okay? Does that make sense? So we've hopefully that's convinced you that VA will only go to VDD minus VT, because after that, the transistor's off, it's not conducting, because my VGS minus VT is now 0. Now let's look at what happens on transistor 2. So this is at VDD minus VT, and we want to see what happens to voltage B. So the current of I drain 2, the second transistor, will be 0 when VGS2 minus VT, just assume it's got the same threshold voltages as transistor 1, because they normally do, is equal to 0. Okay? All right, so VGS, we can kind of choose either one of, whoops, I have no idea what I just did. Get rid of that. Okay, if anyone knows how to get rid of this ruler, let me know. There it is. Okay, thanks. Okay, so for VGS minus VT to be equal to 0, and now what I should really do is I should relabel these. I don't have to, but let's do it for simplicity. From the point of view of transistor 2, we're going to normally consider the source in an NMOS to be whatever has the lower voltage. So this is going to be the drain for transistor 2, and this is going to be the source for transistor 2. okay? Because you consider whatever's the lower voltage to be the source in an NMOS. Okay, so what is VGS for transistor 2? So VGS of transistor 2 is equal to VDD minus VB. Oops. So if I plug that in, VDD minus VB minus VT is equal to 0 when the transistor shuts off. And if I solve that for VB, I get, again, VDD minus VT. Okay? So you don't drop a second threshold voltage. Does that make sense? Yeah, and I see that there's a comment in the chat that basically you lose the second voltage only if you go through the gate, and that's exactly right. The pass transistors here are connected. They're not connected the output of one to the gate of the next. If I connected them like this, so don't do this. You don't want to do this. But if this was your input, this is your first transistor, 1, and you maybe tie that to VDD. And then the output of that, you actually tied to the gate of a second pass transistor. And this is my input 2. Okay, that's going to be a big problem because what's going to happen is your gate voltage is going to be VDD minus VT on this second transistor. And you will drop a second threshold voltage now. Okay, so this, let's call that VC. VC will go only to, it will only swing between 0 and VDD minus 2 VT. Does that make sense? So yeah, you don't want to connect pass transistors this way because then you will actually get multiple drops. The reason you don't get the drop here is the real problem is that the transistor's shutting off. Once your VGS is small enough, it just shuts off. But connecting pass transistors in series like this doesn't make your VGS worse. Connecting pass transistors this way, where the output of one feeds the gate of the other, does keep reducing your VGS every single time. Yeah, so thanks, KP. Thanks for that comment. It's a good idea. So question, can the CAD tool perform routing even before the channel width is determined? Not really. So the CAD tools in tools like Quartus and Vivado are made to target, precisely defined a limited number of chips. Okay, so in other words, they know not just the channel width, but they actually know what is the exact routing pattern and so on. So they know all the wires, all the switches, and they route and they decide whether or not it works. When people are doing architecture investigations, they often leave the channel width as kind of a free variable. So they'll basically say, I haven't actually made the chip yet, so I'm going to run the CAD tool and I'm going to give it different channel widths, and I'm going to see when it succeeds and when it fails. I'm going to use that to help me decide what the channel width is. When you're running a tool in that mode, still every run of the router, you tell it this is the channel width that you're shooting for. You'll just run the router multiple times. So normally a router is always told what the channel width is. Yeah, I can't think of any case where that's not done. So I can't think of a way to perform routing before you specify the channel width. You're welcome.
Hey, Professor, sorry, I just have a simple question. When we do the area of the routing, you know how we had to double it for the vertical and horizontal tracks?
Yeah.
Didn't it already connect to like up, down, and left? Can you just go over why you need a second one? Probably something simple I'm not understanding.
Yeah, basically, okay, so first I'm assuming that the area is dominated by the transistors, not the wires. That's maybe something I should have mentioned. That's typically the case in FPGAs, that they use so many programmable switches that you can fit all the wiring above the transistors. So I'm basically just counting transistor area. And what I haven't shown, but I could, is for this routing architecture, every single one of these wires is going to have a routing driver on it because they're all length 1. So they all have to start in this tile. Does that make sense? I can pick what my pattern is. Maybe my pattern is this wire is going to go this way. So we put the mux going like that. and it might choose from that input and that input and that input and maybe the same output. Does that make sense? Okay, so that's a second wire because my channel width here is 2. It's still got a 4-to-1 mux. It's got some of the like the LUT output is the same one. The wires are different ones. That's my second mux. Okay, but these vertical wires also need things driving them. So let's say one of these vertical wires is going to go up. So I draw like an inverter on it. I didn't really leave myself enough room, but you get the idea, hopefully. And I would draw, a mux going on it with 4 different things going into its mux. Say this and this and this. Does that make sense?
Yeah, that's great. Thank you.
And then the last one, I need to have some that are going down. So I should really have another color. Let's say this one is going down and it has a routing mux up here. And, some of its inputs are going to come from up here, right? Because I need to have some connectivity to things up here. But it doesn't matter. For this repeated structure, what I basically got is 2 wires here. They each need a routing mux, and 2 wires here. They each need a routing mux. So that's W equals 2. So I've got 2 times 2 directions muxes. Does that make sense? The example I was doing before, W equals 12, but it's the same idea. You have to double it for, I've got 12 wires in the horizontal direction that all need some kind of driver and mux, and I got 12 wires in the vertical direction that all need some driver and mux.
Okay, that makes sense. Thank you.
And I'm really counting outputs there. Like, yeah, the inputs came from all over the place so that every one of them got 4 inputs, but I'm really counting how many muxes did I build, and I can't share those. Every wire is getting its own mux and its own buffer, so they can choose what it wants, and then it gets driven with that signal. Does it make sense?
Yeah, that's perfect. Thank you.
Okay, thanks. So if there are any other questions, feel free to ask. Hopefully lab 2 is going well, or possibly it's just got a due date further away than other assignments. So
Professor Anderson's lab is due next week, so.
Okay, so I had a suspicion.
Okay, thanks, Rob. Have a good night.
Okay, good night.